So let's get started with Taylan. I haven't been reading titles, so I'm not going to start now.
Okay.
Your title.
Well, that's well, I don't get it either. So.
Okay.
So I'd like to acknowledge a lot of people actually. So this work has been carried out with Şimşekli was my Ph.D. student, from Bogazici, and we were of course inspired by other colleagues, which we are kind of working together. Basically, so this talk will be about a particular way of modeling audio, which has been popular in the last, say, 6 or 7 years. And essentially, the modeling techniques are based on matrix factorization paradigm, and that we will be somewhat extending and hopefully unifying some of the methods there in the general kind of umbrella under the tensor or tensor factorization model. And I will, in this respect, give a kind of like a probabilistic interpretation or statistical interpretation of this tensor factorization models, and give some example models of existing and novel models for audio analysis for various tasks. And I will describe a kind of a general framework with the hope that you might find it useful also for kind of future work, so that you can also develop new models using this particular framework. And then the talk will lead to the coupled tensor factorizations. That is essentially a kind of a paradigm where you want to integrate several knowledge sources. It's essentially a sensor fusion, information integration type of idea. And if time permits, and if Doug still admits some time, I will talk about a few applications in various fields like tempo tracking and also. I have depending upon the kind of how it goes, I have some backup slides, or I can cut it short. So our main work has been focused in the last couple of years, especially as it's related to audio modeling, in essentially the Bayesian paradigm. So here, what we actually try to do is as follows. So we want to build algorithms by which we can analyze and understand audio or musical structure. And this paradigm is based essentially, you can do it as a kind of inverse synthesis type of approach. So here in this particular framework, we are actually developing models. So that relate the observed audio to the particular structure that we are interested in. And we have typically some prior knowledge about that structure. And once we actually define that model, then the rest is hopefully kind of mechanical. So we can turn the Bayesian handle to actually infer the type of things that we are interested in. And this is in some sense in contrast with some other traditional or algorithmic approach where there is no clear boundary between what and how. So in some sense, these models define what we really want to kind of do, and the inference mechanism is actually how we will be doing it. Of course, these things are inherently coupled. You cannot really write any model and hope to solve it. But anyway, so this is the kind of the general framework essentially that I view things. And so when it comes to analysis of audio, I give kind of just an overview. The main problem, in my opinion, is if you analyze musical audio, is essentially the superposition problem. So you have several sound sources. Even if it's essentially a monophonic source, there can be some kind of a background noise, or if the instrumentalist can do some glitches, as I said, that you might not be interested in. And there is a lot of reverberation problems that you want to kind of get rid of. And if you want to do, of course, music information retrieval, typically, if you kind of develop your features for, say, monophonic audio, they don't apply immediately for polyphonic or mixed sources, because typically, if you compute a feature from this superposition, it is typically not the sum of the individual features. So that's kind of so you need some kind of a separation type of. Another kind of there are of course several applications, but one of the important application in this particular framework is the polyphonic music transcription. Essentially, what you really want is, in this particular application, given a particular representation of the audio signal, here it is a spectrogram, the axis corresponds to time, this is frequency and the energy content at the individual frequency time atom. And that particular representation, we wish to convert to some human-readable notation. And this is actually a quite hard problem. And hopefully this type of models that I will describe also will help to some extent for solving such problems. Okay, so there are many computational issues, like in, for instance, music transcription. I don't want to just read them at this stage. And many actually signal models for audio, also music, have been developed over the time. So this is kind of a very crude kind of classification of those, like time domain, state space, dynamical models. For instance, today morning we saw some of the examples there, like Kalman filter models, etc. Or there are in music information retrieval very much feature-based, like MFCCs or chroma-based, and you can also kind of design hidden Markov models or kind of models on top of this. In this particular kind of modeling paradigm that I will talk mostly on analysis of transform domain. So we have essentially a kind of a Fourier representation, some representation of the Fourier coefficients, and we would like to kind of model the nature of those coefficients. And here we will use a kind of a quite already well-established approach for modeling these things. And so this is essentially, I'm sure that many of you are familiar with this kind of modeling approach. The approach is essentially like this. So the paradigm is based on matrix factorization. Suppose I have a matrix. In this case, in the audio case, it will be a spectrogram typically. And we want to write this particular matrix as a product of two matrices, Z1 and Z2. And here I will explicitly write down kind of the indices, because later it will be useful for generalization, etc. So here X, because it's a matrix, it has essentially two indices here, nu and tau. And in our kind of decomposition, we want to approximate this thing with this product of, again, two matrices. Here I is a kind of a matrix that we are summing over. Here is a kind of a picture of that. So that is, suppose the data that we want to approximate. Here, those red sprites correspond to possibly missing points. So you don't have to observe the whole matrix. In some domains, this is called the matrix completion problem as well. And we want to now describe this matrix as a product of two matrices. Here they are low rank in some sense, so it's a kind of a low rank approximation to that one. But in this particular model frame, that doesn't have to be. You can have also overcomplicated type of representations. So, and why is matrix factorization also quite popular lately? Is because most of the well-known algorithms can also be cast as matrix factorization problems, like, for instance, K-means clustering. By imposing certain constraints upon the kind of individual factors, you can actually develop several algorithms. So that is quite nice. For instance, K-means clustering can be derived in this framework, or NMF, non-negative matrix factorization, can be defined, or PCA, latent semantic indexing, latent Dirichlet allocation, with some kind of variations, can always be cast in this particular framework. So the computational problem here is, in a general sense, we want to minimize actually a kind of a divergence metric between the observed data and this product of two Z1 and Z2. So why this is typically a good model for audio, as actually comes from a very simple observation actually. So like, for instance, if you consider musical audio, typically individual instruments have a certain periodic structure, or the signals which are generated by musical instruments have the periodic structure. And here is a kind of example of a guitar sound. Here is the time and here is the frequency. As you see, you can see the harmonic structure. That is due to the like the harmonics which are in kind of equal space between along the frequency axis. Essentially, this particular matrix describes the energy content, how it varies over the time, and this particular object can be very well approximated with actually even a outer product of two vectors. That is a kind of a very nice approximation, and this can act as a kind of a like starting point for modeling spectrogram. So that is the one of the observations made first by Smaragdes and Brown, and I think Feisha or Larry Saab, who used actually NMF type of approach for modeling. So there is also an underlying probabilistic model to all these things. So you can think of this x, nu, tau as random variables now. And now this is actually, you can think of now this matrix, or this latent matrix in the one factor case, is actually some kind of a parameter of this probability distribution. So you just generate actually the parameter of this distribution in some kind of a factored form. And then given then this parameter as a product, you generate this particular random variable. So that is the kind of the probabilistic. If you have a high rank, so this is for the one rank case, you can think, in some subset of model, not all, but some of them you can think of like this. So if you think about matrix multiplication, essentially you can think of it as a sum of one rank vector multiplications. And then essentially this particular object with 3 indices now correspond to the individual one rank components that you generate independently and then sum them up to actually recover the original audio. So this fits in quite well with source separation, etc. I think where you actually think there are many, for instance, one rank objects that you call the sources and they get superposed and you want to find kind of, given their mixture, the individual components. So this fits in quite well, for instance, in a so-called music transcription problem, where you have a kind of a polyphonic audio, and here the goal is now to represent it, hopefully, with a product of a matrix which looks like this. So here, this matrix contains the frequency signatures of the, say, individual notes. Here is a kind of a piano example. It's the corresponding index to the note index, and this is the frequency. And this is the type of information that we want to get out. This is something which is correlated very much with the musical score. So this is time, and this is which note is being played. So this type of factorization is actually quite useful because many important features can be derived from it. But the problem is just doing it completely in an unsupervised way is typically not successful. So if you just give to this particular spectrogram to your, say, NMF and hope to recover these factors, you typically don't get it unless, yes.
How do you know that those two axes correspond to nodes? Because you're just factorizing it, right?
Yes, exactly. That's what I'm saying now. So this is, like if you actually really can put a lot of prior knowledge about those individual factors and not force them to be.
Oh.
So that is the point. So if you do it completely, in unsupervised, you get a kind of a mixed representation. So that is actually the hope. You want to hope that you recover this particular factorization. Yes, please.
Very good question. Is that the third niece?
Yes. Could you guess it from here or from down? So these factors provide some information, as you see. This is kind of correlated with human perception.
Is that a New York Steinway or is that?
This Masataka Goto's. So, and a lot of work has been done for, actually for deriving factorizations which make also, in some sense, semantically meaningful information. So that is done typically by putting some prior over this individual factors. Many people have tried many different things, and I don't want to go over all the. For instance, here, this decomposition was get by actually coupling the individual coefficients along time, etc. Like enforcing some kind of a continuity. And there are also other ways of doing it by providing some side information. So, for instance, in the standard NMF folklore, that is a typical thing, so that you actually force your decomposition to contain something which correlates very much with the individual spectral templates as well as the musical score. Is suppose you want to decompose this particular spectrogram, in order to enforce that you have as a kind of a template matrix, you also kind of concatenate to this matrix some kind of individual isolated nodes and kind of try to decompose everything together with the hope that you can recover actually something which is correlated with the templates, at least the way you want to expect it. And actually what I will later describe is essentially a kind of a generalization of this idea. So you can think of this actually as like providing side information to the decomposition. Okay, so I have two products, and now this particular template I kind of provided kind of with some side information. The ones who are familiar with Bayesian networks will find this particular representation quite useful. The semantic is slightly different, but the idea is the same. And there have been a lot of work, and some of the models are pretty complicated, as you will be seeing. So, essentially all these models based on factorization of spectrograms, and they are typically highly structured and quite complicated. And like what this framework that I will describe is aiming to is some kind of bringing everything to a common framework, which is very much inspired by probabilistic graphical model, so that you can actually design different audio models and then kind of do inference and that. And here, in this context, I will describe two things that we have developed recently. One is the probabilistic tensor factorization. This is essentially for factorizing individual tensors, and then the coupled version. So that is, and then that's essentially it. So I already said the kind of main research questions, so I go a little bit now technical. So if I talk about tensors, typically I use them as a synonym for multidimensional array. So people who are coming from a physics background might find this term not really very convenient, but it is not very convenient to always say a multidimensional array. So essentially what we will be talking is a kind of an object with several indices. That's it. If you look to the literature about factorization of tensors, some very common models arise, and those are the kind of things you will immediately see, like parafact decomposition. So here, an object with 3 indices, think of a data cube, is factorized in a certain way. This is essentially just if you want to do it, is a simple extension of matrix factorization type of problem. There are other type of decompositions with their respective algebraic properties, etc. And then it's a quite well known and investigated field. And there are several kind of generalization. What I will actually want to tell here is, actually, if you think about tensor factorizations, you don't have to have a multi-dimensional data. Even if you have, for instance, single-dimensional data, it is useful to think in terms of tensors. So here, as a kind of an example, I will talk about the convolution problem, which will actually make maybe this idea a little bit more clear. Suppose I have an observed signal, and Z1 and Z2 Z1 is an original signal that I want to recover, and Z2 is a filter in pulse response that I don't know. And there is some noise again, so this is, in some sense, this is a typical convolution operation, Z1 convolve with Z2, and this is kind of recovering that. So what we will be doing is a very simple kind of substitution. So we will introduce a dummy index D and set D equal to I minus T. And by introducing this new kind of object, the delta Dirac, and then we sum over D, and then we call it yet another tensor. Okay? So in some sense, you have now 3 objects. One, of course, you know it already, but now the deconvolution problem is actually finding these 2 things. So this, of course, doesn't lead to any insight. What will be interesting is now you can hope to model these individual signals in a hierarchical way, and you get actually increasingly more complicated models, for which maybe inference will be harder to do. Okay, how much time do I have?
You have, I was about to give you 5 minutes. So you have 30 minutes total, but I wanted you to stop at 25, so you have
10 minutes?
Yeah, so go until 4:25.
Okay. I have just 4:60. So I have 50 slides more, so this should I'm not joking. So
Okay.
Okay, so for instance, this is a kind of typical situation. For instance, if you have so now I denoted the signal that we want. Suppose this signal is living in some kind of a subspace. So it's a kind of a smoothness constraint that you can fit. And this can be fitted in this framework by just imposing a certain basis and then trying to just recover the expansion coefficient in this basis. So already the model becomes slightly more difficult, and you can do the same thing to the filter, etc. So this is an example of how a kind of a smoothness basis should put. Like here, this triangular basis, a spline basis. Basically, you can actually, by just superposing such basis vectors, a kind of a piecewise continuous signal. So this is a simple kind of modeling idea. So things can become, okay, you can do the same trick over the filter coefficients, etc., and then kind of get more and more complicated models over time. So here is a kind of a example on kind of video how this actually would look like. So we have a blurred image. That's a kind of a very difficult filter. It's just taking the average, and we have the original image here. But if we train the subspace of the images that we want to recover, and also the kind of the filters, if you know something about it. It is typically quite possible to recover something which looks. So this is a kind of a nice way of putting prior information. So now back to audio. There is for instance, a common model which is used quite often for audio. So which tries to circumvent this one rank type of approximation. In audio, typically, if you have harmonic content, that particular content is not modulated by a constant volume. So it's kind of not really parallel. Of course, high frequency coefficients drop faster. So this type of structure can be captured by taking the temporal structure also into account. And that's a model also proposed by Paris Smaragdis. Here the model is as follows. So you have basically two matrices which you now actually convolve with those two basis vectors, and then you get something like this. And the hope is then, given this particular representation, to recover this individual factors. So that is the type of models that one can get. And then on this topic, there have been many different models developed which aim to actually computing different type of kind of factorization. But what is now difficult is, these models become increasingly complex, and it is hard to derive the inference algorithms just starting from the scratch. And that's why we have actually developed for handling this, a kind of a framework which we named the probabilistic tensor factorization framework. And here we describe a tensor factorization model as follows. So we have, in an abstract sense, an object, a tensor, which lives on an index set, V0. So those are the old kind of indexes. You can have several indices here. And then this particular index is actually, you compute a product of several tensor factors, which you collapse over the indices, which are not part of the observations. So that is the general framework for that. So let me give an example. For instance, in this framework, you can describe the NMF model. Here, XF2, so this is a simple matrix factorization model. All indices are corresponding to FTI, and then the observed indices are FT, this V0. The first factor has the indices F and I, the second factors are I and T, etc. And then the indices that we are summing over, the V0 hat, are I. So that describes, in our setting, the entire model. So this is the simplest model that one can think of. And the way we will represent these models is very similar to graphical models. We will apply, again, the factor graph formalism, which is quite well used, in a slightly different setting. Instead of random variables, we will now denote the particular indices, and the factors correspond to this black nose. So Z1, remember, has the elements F and I, so those are not connected to this particular factor. Z2 has INT, so INT is connected to that factor. So that is the description of the model. And using this framework, you can describe several different models in the same framework with increasing kind of complexity. And but now the nice thing is that once a model is described in this framework, the inference algorithm is readily available. So you don't have to derive it from the scratch. So this is not to be mixed with the actual probabilistic interpretation of these models. For instance, the simplest model, NMF, actually, if you write it as a Bayesian network, looks a lot more complicated. So our kind of modeling framework is a lot higher level, so rather than the Bayesian networks. And we have derived for the general factor graph formalism an update rule. So that is essentially, you want to now learn the individual factors in your decomposition. And for the non-negative case, this is a very general update rule. So I will go over that one and then talk about special cases over that. So here, Z alpha is the factor that I want to update, and I fix all the other factors that in a kind of fixed way. And what I have to now compute is the first, a kind of a prediction of the data, which is given by Xset. So that is the actual factors as they are at this stage. And this W is a model-specific kind of function which you actually specify a priori. This is called inverse variance function. It is inherently related to your noise model. And then once this particular model, and the M here is the missing data, And this is the general update. So this delta is a function which has this complicated form, which takes as an argument an object which is on the data space, and all the product of the factors that you do not want to update at this stage. And to the trained eye, this actually looks like a marginalization operation. So you multiply all the factors and all something which is related to the data, and sum over the indices which are not part of the factor that you want to update. So that is the general description. And we have also update rules for general data. So let's see how that looks for the NMF updates. So you first calculate the kind of prediction over nu and tau, and then you take out Z1, compute a pairwise marginal over nu and I. That can be done actually conveniently on this factor graph, and you iterate basically. So that is the essential algorithm specialized for NMF. You can also put some priors over the individual factors. The update rules are analogous. And so I will jump to I will need 2 more minutes and then play some. So now this particular framework can be generalized in a convenient way to actually factorizing several tensors at the same time. So here the problem is slightly different. Suppose you observe several things. So those can be in some sense like information which is complementing each other, similar to the NMF problem I showed you in advance. Here, some of the factors are shared. So you can actually now ask, how do I compute these individual factors? And for that particular problem, we can actually define an analogous update rule. So it is very similar to the first one. With the only difference is there is a kind of an indicator matrix R nu alpha. This is very simple to construct. The way we construct this, it is essentially the adjacency matrix of this graph. So we just ask, is A member of X1? Yes. If it's yes, we put a 1. Otherwise, we put a 0. And that's a kind of a known matrix. And this update rule is again available in a kind of a constant. So you can actually, by using this algorithm, compute the individual factors. Now, to cut it short, I will describe an application of this particular framework and then finish. So here the problem is we have a musical audio where we actually are missing several frames. And for instance, in a standard NMF framework, this is impossible to recover. But by hoping to provide side information, we might actually recover the actual audio signal. So this is the tensor factorization model that we have come up with. So here is the audio with the missing bits. Here we provide a side information, some spectrogram shapes from, say, a piano, if you know this is a piano piece. And the interesting part of this model is we also provide side information from musical scores, which are viewed again as matrices. And the idea here is that, well, if you have a musical score, there is some harmonic structure which is repeating itself. So that can also be represented conveniently using a factorized structure. So I don't want to go into details of that, but this idea is, in some sense, this particular data is providing side information to the spectral templates, and the scores are providing side information to excitations, which hopefully should correlate with the scores. So when we actually do this and then run the general kind of update rules.
You can do your demo?
Yes. So this is the
I need to go louder. Are you able to go louder?
I'm loud enough, I think.
Well, you should pull the unhook the monitor.
This one?
Yeah. Gotta take care of our ground.
So this is the missing. I played it again. Probably you can guess what it is, but so this is the deconstruction. Also, first I play the reference score. So that's the score that we give to this. So this will hopefully provide some information about the general structure of musical scores. And this is the reconstructed version. And this is the original, so that's the...
Yeah, it's the audio's too loud. We can hear you in another room.
Okay.
Okay. That's good, so...
We're gonna have this session in like a garage.
Okay, so I just summarize in 1 minute. So we have developed a method for actually computing quite a large class of factorization, which are useful especially for audio analysis, but also probably also other applications. And there are other extensions possible. You can also do Bayesian treatment, full Bayesian treatment if one is interested in that. We have a toolbox currently in the alpha form. So you just specify a kind of a model, like you specify a graphical model, and it computes for you the factorization. So it is not currently supporting the coupled case, but that will come soon. And this is, quite fresh out of the oven. And if you are interested more in reading this particular framework, I have a few references, and I'm happy to take any questions if there is time for that.